Right, part two. So we have just seen the structures of purines and pyrimidines. We have seen how adenine looks like, how guanine look like, how xanthan, hypoxanthin, and uric acid looks like. Then we have also seen how some of the pyrimidines like cytosine, uracil, and thymine will look like. Now we'll see some important medically relevant purines. So medically relevant purines are xanthan, hypoxanthin. Xanthan, where do we come across xanthan in uric acid metabolism? Hypoxanthin in salvage pathways, as well as uric acid metabolism. Uric acid is the end product of purine metabolism. Then where do we come across caffeine? Where do we come across caffeine? Caffeine, coffee, tea, cocoa, all these are purines. Then we have our 7-methyl guanine, a specific type of guanine that is present in the cap of mRNA. The mRNA cap is made up of 7-methyl guanine. To this 7-methyl guanine, the adenine is attached, which is characteristic adenine. We'll talk about that when we are talking about this DNA structure and RNA structure. Then we have this S-adenosylmethionine. S-adenosylmethionine or Uncle Sam, we have seen in 1-folate metabolism. S-adenosylmethionine is formed from methionine, and this is the methyl donor of the body. Then active sulfate, which is a sulfate donor. Cyclic AMP and cyclic GMP, these are second messenger systems. Specifically, cyclic GMP acts with nitric oxide. Then we have our vitamins like NAD, nicotinamide adenine dinucleotide, nicotinamide adenine dinucleotide phosphate. Then we have flavonoids like flavin adenine dinucleotide, niacin, and riboflavin, both coming here. Then another enzyme, coenzyme A. So the coenzymes are vitamins. Question is vitamins which are purines. Vitamins which are having coenzymes which are purines, they are niacin, riboflavin, and coenzyme A. 3 vitamins are having structures which are purines. Then we have this drug allopurinol. Allopurinol, xanthan oxidase inhibitor. Inhibitor of xanthan oxidase. We give in treatment of gout and Lesch-Nyhan syndrome and tumor lysis syndrome, other syndromes where we need to decrease the uric acid level, especially in all hyperuricemic conditions. We give allopurinol as a first line drug to decrease the uric acid levels. Then we have 6-merpactocurin, 6-thioguanine, azaguanine, and azathioprine. These are chemotherapeutic agents and immunosuppressants. Like suppose there is organ transplantation and you need to suppress the immunity to prevent the graft versus host reaction, then we need to suppress the immunity and we give immunosuppressants. So all these drugs are used as chemotherapeutic agents. Chemotherapeutic agents. All right, so those are medically relevant purines. Coming to medically relevant pyrimidines, we again have chemotherapeutic agents. Almost all are chemotherapeutic agents. 5-fluorouracil, cytosine arabinoside or cytarabine, 6-azathioprine, all these are chemos. Whereas vitamin which is a pyrimidine is thiamine. Vitamin B1 is thiamine, whereas vitamin B2, B3, and coenzyme A are purines. All right. Okay, so what are the properties of these nitrogen bases? Remember, we are talking about properties of nitrogen bases, not the nucleosides. Nitrogen bases, that is adenine, guanine, cytosine, uracil, and thymine. What is a importance, or what are their properties? First thing, we know they are heterocycles, they are having nitrogen. Second thing is they act as weak bases and their pKa values are 10 to 11. Remember, nitrogen bases, we call it as bases because they are basic. Okay, so nitrogen bases, adenine, guanine, cytosine, uracil and thymine, these are basic in nature, but the nucleotides that they form, they are acidic in nature. Okay, then these are planar structures. They are planar structures, they are not globular. So if they are planar, you can just stack them. You can just stack them one above the other. You can just stack them one above the other. All right, so that is how DNA gets stacked one above the other. They are planar, so they can be stacked easily. All right, so coming to isomerism or tautomerism that they follow, oxo and amino groups of purines exhibit keto-enol and amine-imine tautomerism. Although physiologically conditions, amino and oxo forms are more common. Now I'll let you know through diagram what exactly we mean. Now we have seen that adenine has an amino group on the top. Okay, adenine as well as cytosine both have an amino group on the top. All right, this amino group can exist in an imino form also. It can exist in an imino form also. Amino, imino tautomerism. If we look at guanine and uracil, we see that there is a keto group. There is a keto group, say guanine or uracil or thymine. They are having a keto group on the top. This keto group can exist as an enol form also. This can exist as an enol form also. Keto enol. So this is the tautomerism that we were talking about. Amino tautomerism, amino-imino tautomerism and keto-enol tautomerism. Remember, this is happening in the nitrogen bases, not the nucleotides. Don't get confused with nitrogen bases. Okay, don't get confused with nitrogen bases. Don't get confused with the nucleic acids. We are talking about the nitrogen bases only. All right, so here the amino as well as the oxo or the keto form, these are the ones which are most commonly present in the environment, but they can also exist as an amino and enol form. Okay, so that is the amino-imino and keto-enol tautomerism. So properties, let us look at them once again. They are heterocyclic, they are basic, they are planar in structure, and they exhibit the keto-enol and amine-imine tautomerism. Right? Then what are nucleosides? First, we had seen nitrogen bases. We have seen nitrogen bases. They are either purines or pyrimidines. Then we have seen different types of purines, adenine, guanine. Then we have seen different types of pyrimidines, cytosine, uracil, and thymine. And we have seen their four properties. What are they? That they are basic, they are heterocyclic, they are planar, and they exhibit amino-imino and keto-enol tautomerism. All right. Now let us come to nucleosides. What are nucleosides? Nucleosides are basically these nitrogen bases bound to a sugar molecule. So nucleosides are nothing but nitrogen bases plus sugar molecules. So there are two to three types of sugars that are attached to these nitrogen bases. One is ribose sugar, a deoxyribose sugar, which is deoxy at second position. Then we have this is 2' 3' dideoxyribose, which is used in Sanger sequencing. This is seen in Sanger sequencing. To stop the Sanger sequencing, we use 2,3 dideoxyribose. Okay, so mainly you have to remember D-ribose and deoxyribose. Ribose we use in DNA and deoxyribose is present in the DNA. Now what is the bond present? The bond present is beta-N glycosidic bond. It is a glycosidic bond. It cannot rotate. There is no freedom of rotation. There is no freedom of rotation. Very strong bond, very rigid bond. There is no freedom of rotation around this. It is between C1 prime of ribose or a deoxyribose and N9 of a purine, and C1 of ribose or deoxyribose and N1 of a pyrimidine. We'll see what we mean by this. Now, okay. So let's say this is adenine. Okay, let us number this 1, 2, 3, 4, 5, 6, 7, 8, 9. So N9, this is the one in pyrimidine, sorry, in purines. I'll draw a purine here. We'll number this too. 1, 2, 3, 4, 5, 6. So it is always N1 in a pyrimidine and always a N9 in a purine. This N9 in purine and N1 in pyrimidine, these are attached to sugar molecules. These are attached to sugar molecules, a ribose, this is the glycosidic bond. It is occurring between C1, C2, C3, C4, C5. Okay. So C1 prime, C2 prime, C3 prime, C4 prime, C5 prime. We use the prime for numbering the sugar. So this is a ribose sugar. So this is ribose sugar, and on the C2 carbon, the hydroxyl group is changed to H. If it is OH, it is a ribose sugar. If it is OH, it is a ribose sugar. So this is adenine. This is adenine, and this is the ribose sugar. So adenine, a purine, that is adenine plus a ribose sugar, it becomes adenosine. It becomes adenosine. Suppose I remove this, OH. Now it becomes deoxyribose. So this now becomes adenine plus deoxyribose, which is deoxyadenosine. This we see in DNA, deoxyadenosine. Adenosine we see in RNA, because RNA uses ribose sugar and DNA uses deoxyribose sugar. You understood the difference? What is the difference between a ribose and a deoxyribose? So a purine is always attached to N9 with the sugar. Sugar can be a ribose or a deoxyribose. The deoxy nature of it always occurs at the C2 carbon. Now same thing with a pyrimidine. sugar is attached,